Alright, we're going to talk about limits and what it means to say that a function is continuous. So limits and continuity. You know what it means for a function to be continuous. I think that probably you could explain to your little cousin who's in the first grade what it means for a function to be continuous. If you could get them to understand that a function is this sort of, squiggle that you draw on your graph, then it's pretty easy to understand that a squiggle that you can draw, we draw our little arrows on the end to represent that it just keeps on doing whatever it's doing forever. If you can draw the squiggle without taking your pen off the paper, or your pencil, or your quill, or whatever you're using to write with, then you can say it's continuous. So what does it mean for something to be discontinuous? There are three classifications of discontinuities that we're interested in. The first and the least offensive of the three is when you have a function that's going on and it looks like it's going to be a continuous function, but there's just one little point missing. And of course this little circle is a grotesquely large representation of what's really happening, right? Really there's just one infinitesimally small, tiny little point missing. And hopefully you've had the experience with your calculator that if you graph something that has a hole in it, you will not be able to see that hole with a calculator because it's so tiny. More about that later. So we'll call this is a hole. Function can, and we still call it a hole whether or not there's like a point that seems to be in the quote-unquote wrong place. Then we have functions that go along minding their own business, and then all of a sudden there's a break in the function like this. Maybe we should discuss, just go back to this one for a second. Does this hole prevent it from being a function? Does that somehow violate the principle or the conditions that a function needs to satisfy? And the answer is it still is a function, right? Because it still passes as we vertically scan across this. We never hit 2 points at the same time. Even if there's like a misplaced point, we're still only hitting 1 point at a time. Likewise for this one, although it's kind of strange looking maybe, we still, because that's open and that's closed, we still only ever hit 1 point. So it's still a function. We'll call this a jump. You could call it a break, and the vocabulary isn't really important. But we have holes, jumps, and then the worst kind of discontinuity, I guess, and I say worst in terms of having any chance of repairing the function into something that is continuous, is when you have a vertical asymptote. Sorry, I didn't mean for that to look vertical there. So you're shooting up to infinity, and whether or not they're both going up to infinity or not, it's going to be pretty serious problem in the function here if you wanted to repair it. So say vertical asymptote. Right. So those are the three different kinds of discontinuities. Lots of functions that you know don't have any of those problems, right? So we could just think for a minute. Some examples of functions that have no discontinuities. polynomials, all polynomials, right? Trig functions, but not all trig functions, right? Actually just sine and cosine. The other ones have vertical asymptotes. All of 4 of the other ones, right? The natural log function, the e to the x function. What other functions should you be familiar with? I think those are the big ones that do not have any problems. All right, now what does this have to do with limits? Well, turns out the definition of continuity at a point, we'll call the point when x equals some number c. If you want to be able to say that a function is continuous at point c, then that function has to meet the following 3 criteria. Number 1, f of c must exist. In other words, if there isn't even a point in the domain of the function that goes with the value you're talking about, you don't have a chance of being continuous there, right? You have to have a point there. The second criteria is if you want to be continuous, then the limit as x approaches c of your function must also exist. Come back to that one, what that means in a second. And then the final criteria is that those 2 things must be equal to each other. Those 2 things, limit as x approaches c of f of c, of f of x, this must actually equal f of c. So what is this preventing? I think this is preventing the first condition. It's preventing the worst kind of discontinuity. In which of these 3 cases does the value not even exist? On this one, right? If this is our value, if this is the c we're trying to plug in, then this is this condition prevents vertical asymptotes, right? By saying that f of c actually exists, forcing a point to be there, that means you're getting rid of that vertical asymptote problem where you're dividing by 0 and there is no point at all. What does this do? Well, saying that the limit as x approaches c of f of x must exist, notice that there's no plus or minus here. That means that the 2 sides must be, whoops, that's hard to do looking at the screen, there we go. The 2 things must actually be coming into the same thing. They could be coming into a whole, right? But they couldn't be doing this, because here the limit here would be, oh, I don't know, 2 or something, and this limit might be like 1/2 or something. There are different things on different sides. So by saying that the limit as x approaches c of f of x must exist, we're forcing the 2 sides of the limit to be the same, and that is going to prevent jumps. And then last, by forcing the 2 things to come together and making sure that there's a point, if we make sure that the point is actually in the hole, right? This is the point, this is the place where there could be a hole, then we're plugging that hole and we're preventing that kind of discontinuity. So, in order, our 3 conditions prevent vertical asymptotes, jumps, and holes in functions. And notice that 2 of those are conditions that are defined in terms of limits, which is a new concept for us. So although continuity is very intuitive, because you can always just go back to the can I draw it without taking my pen off the paper. But here now we have a formal definition for that, and the conditions, the way that we describe those conditions, we use our new concept of a limit. All right, so what kinds of things we do here? We could answer questions like this. Where is the function f of x is equal to x squared minus 1 continuous? And think about that for a second. The answer is everywhere. This has no problems. You might start suspecting, and you would be correct, that investigating the continuity of a function is a lot like investigating the domain of the function, right? We're trying to figure out if there are any issues with the domain. And of course, this exists everywhere. There's no holes, jumps, or vertical asymptotes. So how about this? Where's 1 over x continuous? Well, it's continuous everywhere except 0, because there's a vertical asymptote at 0. Right? So two ways to look at that. You could say anytime you have a rational expression like this, you should, a little alarm should go off, like watch out for the bottom being equal to 0. You know that causes a problem because you can't divide by 0. So you could look at it that way, or you could imagine the graph of this. You should be familiar with that graph, of course. And you could say, well, I know there's a vertical asymptote at 0. Either way. How about the function here's a piecewise function, right? You know how this works. Which, if you want to find like f of something, where should you plug it in? Into which piece? Well, it depends. If the x you're trying to plug in is less than 2, then you use this rule. And if the x you're trying to plug in is greater than or equal to 2, then you plug in this rule. Now, looking at this piece taken on its own has no issues. It's just a straight line that would be continuous everywhere. And this piece is just the squaring function. That has no issues. So the only possible issue this could have is if the two pieces do not link up, right? This is the piece that's going to have the open circle. This is the piece that's going to have the dot. But the dot must go in the open circle if we are going to avoid having a jump. So how do we determine that? Very easily. We plug 2 into this and plug 2 into this and see if we get the same number. Now, if you object, if you're thinking, wait a minute, you can't plug 2 into this because there's no equal sign there. It doesn't matter. We're checking to see this is the hole at 2 and this is the dot at 2, and we need to make sure that they're in the same place. So 2 plugged in here gives me 5. 2 plugged in here gives me 4. So this function is going to have a hole, and then it's like it missed. It was kind of close, right? We're only off by 1, but there is in fact a jump in that function. So this is continuous everywhere except for 2. Right? And using, if you like to use that interval notation, you could say, instead of saying x equals 0, you could say that it's continuous. You could describe it like that, right? Saying not 0 is the same as saying this. The open interval here indicates that 0 is not included. Likewise, you could say, if you wanted to, you could say that this is continuous on those intervals. So watch out for all the issues that you've been taught to look out for since Algebra 2. Watch out for square root signs. Watch out for absolute value signs. Watch out for piecewise functions where they link up. Watch out especially for denominators and where they are equal to 0. You'll have some practice doing problems like that. Now here's an interesting type of problem. you one example of this. Now find k so that this piecewise function, f of x is equal to, let's say, I'll sort of clone the one from the last example. So is it possible to find a value for k that would make this function, this piecewise function, continuous everywhere? In other words, can we eliminate this jump problem? Well, how do you do that? Well, the same way we tested, when I plug 2 into this and 2 into this, the only way it's continuous is if those two things are equal, right? If the whole gets plugged by the point right there. So plug 2 into this, I get 5. Plug 2 into this, I get 4k, right? The only way it's continuous is if those two things are equal to each other. And so that happens when k is equal to 5/4. A couple problems like that in the book. Now, I'll just tell you about something called the intermediate value theorem. Heretofore referred to, or henceforth. What's the right thing to say there? From now on, how about that? From now on, I'll call that the IVT, intermediate value theorem. What could this possibly mean? Intermediate just means like in between. Value is in the value of a function. This is the first of, let's see, I can think of 3 off the top of my head, what we might call existence theorems. These are theorems that talk about some point having to exist without necessarily giving you a way of finding that point. So here's what it says. It says that if a function, f of x, is continuous, we know what that means now, right? Well, we kind of knew what it meant already, but now we have our formal definition. If f of x is continuous on a closed interval, a to b, then there must exist a point we'll call the point c comma f of c. Right, that's a point c comma f of c. That's like the x coordinate and a y coordinate, where c is in the interval a to b. Right? There's got to be some point in between a and b. Such that, I think I missed a little detail here. If f of x is continuous on AB, then there must, and I'm going to insert something here, right? And let's call some value, what shall we call it? How about, let's call it d, right? Some number d is between f of a and f of b. All right, so sorry about that being out of order, so let's start from here again, read through. If f of x is continuous on the closed interval from a to b, and you've got some number that's between the y values, right? I don't actually know. I couldn't put it as an interval because I don't know which one of these is bigger, right? The function could be going up or down, so, but d is some number that's in between those y values. Then there must be a point, c, f of c, where c is in here, such that f of c is equal to that number d that we picked. All right, well, that's your first example of what theorems look like in calculus and in all math from calculus and beyond. They look difficult to understand, and they're written in a very highly dense, efficient language that has lots of symbols. And if you were to look this up in a calculus book, like a college calculus, like a real analysis book, it would be even more dense than this, and there'd be even more symbols. So what the heck does it mean? Well, maybe you could pause for a minute and just sort of mull that over. It actually means something that's super, super intuitive and maybe so obvious that you might wonder why anyone would ever bother saying it. Never mind in such complicated, dense, obfuscating language. So think about it for a minute. All right, translation. We've got a continuous function, and it goes through the points. Let's say this is the point a comma f of a, and somewhere over here is the point b comma f of b. What this says is that if you pick any number between f of a and f of b, so like somewhere in between these we have our d, right? It doesn't have to be halfway in between, it could be anywhere in between. There's the d. What this says is it is not possible, if this function is continuous, you cannot get from here to here without having a point that actually has this y-coordinate, right? So, I mean, try, right? You could try to draw a function that's continuous from here to here and not cross the line y equals d. You can't do it. So here you can try to avoid it, but eventually you're going to have to cross if you're going to get to here, right? Now listen, it would be possible to get from here to here without crossing that line if you were allowed to have a hole or a jump or a vertical asymptote. Then you could do it, right? But if you're continuous, then you can't do it. Every single y value in between f of a and f of b, every y value has to get hit by some x value. So here's our point. What would the coordinates of this be? We would say this is the point c, comma, f of c, where f of c, the y value, was equal to the d that we were talking about. So that's what the intermediate value theorem says. It's an existence theorem. It doesn't tell you what this point is. It just says that if you're going from here to here and you know the function's continuous, then you must cross every single y value in between f of a and f of b. There's got to be an x value that goes with any y value you can pick between those. That's what it says. Here's one quick application of that. If you have a function, for example, let's say f of x is equal to, trying to think of an example off the top of my head. Let's try this. Oh, I don't know if this is a good example at all. But but we can try it. Let me just graph that very quickly before I waste any of your time. So this is, I would ask you to do this without graphing, but I'm just going to check and make sure here that this is a good example of what I'm talking about. I'm going to make sure, since I'm in calculus class, that I am in radian mode, and I am. And then I'm going to go ahead and graph, sorry, my calculator in a weird mode here. That window should do, let me just go up to 2. All right. All right. Oops. Sorry about that. I'm not super crazy about that example now. Well, one could make this argument. If you can find a point that makes this positive and another point that makes this negative, then if you know this is continuous and this is continuous, then there must be a zero of this. In other words, if we take this, if we're looking for zeros, zeros of a function are, of course, places where the function is equal to 0. Right? So if you're looking for a zero of this function, that would be the same as doing this. Right? Well, you could try plugging some numbers into this. Like, for example, you know that the natural log of 1 is 0, right? What's f of 1? Natural log of 1 minus the sine of 1. Natural log of 1 is 0. And I don't know how familiar you are with radians, but what's 1 radian? How much is that? I mean, what the heck is a radian anyway? Well, radian measures, it's just like measuring the circumference. Instead of measuring an angle, like say 90 degrees or whatever, it's measuring that same angle by talking about how much of the circumference of the unit circle you've gone around. Now, the whole circumference of the unit circle is 2 pi r, or in other words, it's about 6.28, 2 times pi, right, since the radius is 1. So 1 radian is about a sixth of that. 1 radian is, it's about 60 degrees. It's more like 57 degrees. But anyway, point being that the sine of 1 is about, it's about square root of 3 over 2-ish. It's some positive number. So 0 minus some positive number is equal to a negative number. Right? There's no question that the natural log of 1, which is 0, minus the sine of 1, which is some positive number, because it's an angle in the first quadrant, is negative. Then we could try plugging in something else, like if we go here, this might freak you out a little bit, but if you have to do an example of this, it will be a little bit easier to pick the points, I think. Let's try finding f of the number e. Let's see, that would be the natural log of e minus the sine of e radians. Now that's like 2.7 radians. Well, let's look at the circle here. This is 1 radian. This is 1.57, or pi over 2 radians, right? This is about 3.14 radians. So sine of e, that's about 2.7. So that's going to be somewhere over here, right? So it's some positive number between 0 and 1, right? That's e radians. It's certainly between this and this, right? So the sine of that, that's the y-coordinate on the unit circle. That's going to be some positive number between 0 and 1. right? What's the natural log of e? Well, the natural log of e, that's like asking, what do you have to raise e to get e? It's 1, right? So that's 1 minus some positive number that's less than 1, right? Remember, it's between 0 and 1, and that gives you a positive number. So what does that mean? It means that when I plugged in 1, I got some negative thing, right? Exactly what was it? I don't know, some negative number. And when I plugged in e, I got a positive number. Now, this is a continuous function minus another continuous function. This does not have any holes, jumps. It does have an issue here, right? Because the natural log function stops, so it doesn't exist over here. But once you clear 0, then you've got continuous function minus continuous function. That's continuous. So that means to get from here to here, I have to cross 0. So that means this function, f of x, must have a 0 between 1 and e. It must. And then we could verify that by going back to the graph, saying, well, there's the 0 right there, right? You can see it. So we could find, so I can calculate the 0. It's somewhere between, looks like 2 and 3 on this graph. So it's at 2.22-ish. And in fact, that is, of course, between 1 and, this is by 2.7. So it didn't tell us what the 0 was, but it did tell us that if you're going from negative to positive, you've got to cross the x-axis. So that's just an example of one thing that you cannot do, or one way that you can sort of ground that theorem in a real example. All right? And then picking these points, of course, the art is how do you pick these points so that you can actually get a negative and a positive. And I made one up where it was maybe a little bit tricky to pick those, but maybe not too bad. All right?